Alright, so today we're going to talk about limits. We're going to review our limits. More specifically, we're going to be finding our limits numerically, graphically, and algebraically. Alright, so does anybody explain to me what a limit actually is? What does a limit do? Are you serious? Alright, so a limit, anything? Anybody? Kinda like a maximum. So here's the thing. When we evaluate an equation, does everybody understand what I mean by evaluate, right? It means you plug in x and you get a y, right? So if you plug in 2 and you get 4, then 4 is the evaluation of that equation, correct? But when it comes to some things, can we plug it in? Can we actually plug in a value into all equations? No, so we get something that's called a limit. A limit is more of a trend. Basically, it says, look, I can't plug in, for instance, 2 into my equation because maybe there's an asymptote there. But as I'm approaching 2, I'm going towards this value, okay? So that's what a limit is. A limit is essentially, um, sometimes it's a direct evaluation, but sometimes it's, look, this is what it's trending towards. This is what it's going towards, okay? So that's a limit. You've done this before, and you're going to need a calculator. So, okay, so if you were in my summer pre-cal, you remember doing this exactly, right? So what we're going to do is, the first thing is numerically. And when I say you're finding a limit numerically, what you're doing is you're essentially building a table, right? And based on that table, you can see a trend, okay? So it's actually really, really simple. So it says use your calculator to complete the table, then use the results to estimate the limit, then graph the function to confirm your results. Well, the calculator is going to do most of the hard work for us. Like, so here we go. I have this equation. Can somebody read this for me? Of all that, right? So exactly, that's what I wanted to hear. This is the limit as x approaches -3 of this function, right? It's a limit as x approaches -3 of this function. Now, why do I have to use a limit here? Because what would happen if I plugged in -3? You get a 0 in the denominator, which means it is undefined. So this is why we have limits, because I can't always plug stuff in, right? So uh, what we're going to do is we're going to see, okay, fine, might not be able to actually look at -3, but I'm going to look at the numbers around -3 to see if I can see if they're all trending towards a certain number, okay? So here's what we're going to do. We're going to build our own table. Do you guys know how to build your own table? Okay, so go to your calculator. Okay, I would clear it, so make sure nobody mess with it. And then you're going to go, of course, put your function in. So our function was what? Help me out. It was the square root of x plus 4 minus 1 on the outside. Okay, over x plus 3. Is that correct? Okay. Um, I can graph it. So not a very good graph. I'd probably have to zoom in here. Still not a very good graph. You can box. So you see, basically, it looks like, so because of that square root, do you see what it's supposed to look like? It's supposed to be like a radical. So I don't know if you can tell, but it's going to kind of goes like this, right? It kind of trends, and then you see how it's like that. Did I put it in wrong? Did y'all put it in wrong? Yes, right? Shouldn't it be? And the reason I know the -1 is outside is because wouldn't they just say +3 instead of +4 -1, right? So you just you press the right button. It'll get out of it. Okay? So anyways, notice my table. So look at all these points. Okay? What are they doing? They're getting closer to -3, right? Obviously, I don't want to look at -3 because we already said it's going to be undefined, right? It's going to be an error. So we're going to get closer and closer to negative 3 from both sides. From both sides. So I'm getting closer and closer to negative 3 from the left and from the right. Okay? So how do I do this? Because if I go to my table here, it's whole numbers. Good. I table set. So second window gives me my table set. And all I'm going to do is switch my independent, which is my x coordinates, on ask. Okay? And then now, guys, plug in um, the values that you want. So you can plug in any x value, and the calculator will give you the y. So as you're getting these values, can you tell me what they are? So negative 3.1 gave you what? 0.513, is that right? Yes. 0.5131717, sorry. 5317. What about negative 3.01? 0126. What about negative 0.3001? Okay. What about negative 2.999? What about negative 2.99? Yes. And what about negative 2.9? Okay, so is there a trend? Is there a trend? Now notice I'm going from both sides. So as I'm approaching negative 3, what is this thing doing here? What? Okay. All right. So I know at negative 3 there is an asymptote, right? There is an asymptote. But what am I approaching? What am I approaching? Half, right? 0.5. So that's the limit. It's that simple, guys. It's that simple. Okay? So all you're doing is numerically, so you're seeing what the numbers are trending towards. All you have to do is fill out. Now, am I always going to give you the x's? No, so it's up to you. Now, notice the x's that I chose. For some reason, some students are like, well, I'm going to choose negative 4. And it's like, well, that's okay, but is that close to negative 3? Not really. If you want to be technical, it's an infinite amount away from negative 3, right? Because I can technically have an infinite amount of decimals, okay? But, so you want to get as close as possible. You want to get as close as possible. Very simple. So if this is 1, I know as I'm approaching negative 3, it's somewhere around here, okay? And I think we saw the graph look like that somehow, okay? Any questions on numerically? We've done this, right? So this is a review. Okay, do me a favor and try this one on your own. Try this one on your own. Give you some time to try this one on your own. All right, so I don't think that most of you will choose the same values. Everybody's values should be different. But give me some values that I can choose. First of all, does everybody realize why I cannot plug in, right? Obviously, 0 will be on the bottom, okay? So give me some values that are getting close to 0, but not necessarily at 0. 0.4, but that would be on the right side, right? Because that's positive side. Because remember, I have to approach 0 from both sides. So I need some negative, some positive here, okay? You said what? Positive or negative? So negative, she said negative zero point 0.1. Okay, so then what did that give you? Okay, and then what else did you choose? Negative zero point 0.01. Negative zero point 0.01, and then what did that give you? Oh, okay, so what was this one? It's fine, you're fine. 3.8942, okay? So then I'm assuming the next one you chose was negative 0.001. And if your calculator was like mine and just got frustrated and tells you what? 4. It just tells you 4, right? It's like I'm not going to keep putting more 9s. It's basically 4. Okay, so then at the other side, yeah, it should be this one but positive, right? If you're doing it like this. Like I said, I'm assuming that most of you have um, different ones. So they might be a little further away. You might be going by halves. You might be going by twos. It doesn't matter. You'll get the same. And then this one told you also 4. Is it the same thing? Just positive? Or no? Same thing? Because okay, so good question. She said, why are they both positive? You know, because remember, you're just approaching 0, and it's the same value. So it wouldn't make sense just that you were approaching 0 from the right and it's positive, but you were approaching from the left and it'd be negative, right? So if you looked at the graph, did y'all look at the graph? So it's a sine graph. Do we all know what a sine graph looks like? It's a wave, right? It's a wave. So if you looked at the graph, it has the normal sine wave like that. But then as you approach 0, it jumped up here. Okay, and so this is obviously what? 4. Okay, so that is what the graph, so the limit as x approaches sine of 4x is equal to 4. Simple as that, simple as that. So numerically, this is just one method. It's not the only method. This is a good method to have because sometimes with the other two, it's not always an option. But so looking at the trends of the numbers is always a good method. Again, it's just you want to get as close as possible, okay, with just so there's not so much error. So I would not choose like, since it's going to 0, I wouldn't choose 2, 1, half, you know, because those are a little too far away. So you want to get as close as possible. Any questions on finding it numerically? All right. So the next step is to graphing, is to graph. Okay. Sometimes graphing is a good way to find a limit. So first of all, I have this function. It's called, what kind of function is it again? It's a piecewise function, meaning it's pieces of different functions, right? Not the whole functions themselves, but pieces, all right? So I have here, I have x squared plus 1. What is that? Can you tell me what that is? It's 1 up. Again, so this is a parabola moved 1 up. Again, how can I tell the difference between moving up, down, left, or right? Parentheses. If it was left and right, it'd be inside of parentheses, right? And then you always do the opposite of what the sign is in the parentheses. So in this case, no parentheses at all. So this is just a parabola moved up. Um, so moved up 1. So then my parabola looks something like that. Okay? The only difference is, or what's my condition here on this function? X does not equal to 2. So what does that mean right here at x equals 2? What does that mean? There's a hole, okay? It cannot be equal to that. So there has to be a hole. That is not an eraser. So there has to be a hole. So at 2 basically looks something like that. Okay? And then here, it says 3. Just 3. At x equals 2. What kind of function is just 3 at x equals 2? You were right. It's just a point. Guys, remember, these are y's, right? So when x is 2, y is 3. So that is a single point. If it were going to be um, a line, and the reason, actually it should be a line, but the condition is only at one point. Okay? The condition is only at one point. So at x equals 2, it's 3. Now, first of all, um, I know that this is 1, right? My scale might be off a little bit here. I know this is 1. Can you tell me what where this hole actually occurs? Well, 2 on the x-axis, but can you tell me what y value this is? 5, because it's 2 squared plus 1. It should be 5. So this is 5. So I can kind of see my scales a little bit off, because now if this is 1, then that's 5. So then it's 2, 3, all up in there, right? So 2, 3, 4 are somewhere in there. So um, at 2 comma 3 should be somewhere, according to my picture, should be somewhere right here. I'm just kind of drawing away. So basically, you realize it's just a point, but it's not on the graph, right? It's not on the graph. Depending on where yours is, it's not on the graph, okay? So what is the limit as x approaches 2 of this function? What is the limit as x approaches 2 of this function? So remember, the limit is what is it approaching? What is it approaching from both directions, the left and the right? So as I'm approaching 2 from the left and the right, what's happening? Where are they going? To the hole. So is that okay? Can a limit be where a hole is? Yes, because it's a limit. It's not a direct value. Okay? Remember, the definition of a limit is what is this graph or function trending towards? Not necessarily what is it right there. Okay, so these are trending towards 5. Even though we know that there's a hole right there and there's not an actual point. So limits don't have to have actual points. They are trending towards that value, that y value, okay? Any questions on that, on graphing? It's pretty simple, okay? You've probably, oh no, don't look. Okay? Why don't you try this one on your own? Now I have to go. This function here, does it look familiar? You actually had one similar to it on the homework, okay? You had one similar to it on the homework. And I'm asking you to graph this, so you probably just stuck it in the calculator, right? You probably just stuck it in the calculator. So, can you tell me what kind of function is this, by the way? It is a rational function. Good, it is a rational function because it's a fraction, right? It is a fraction. However, inside my rational function, I have a what? An absolute value. So it's kind of weird because we have this idea that rational functions should be nice and curved, right? Two separate pieces, nice and curved. One like that and the other one like this. But then we also know that a absolute value looks like what? The V graph, right? So it looks like the V graph. So it's kind of hard to try and put those two together. And when you do, you get this graph. So if you put it in your calculator, you notice that you got something that looks like this. Okay? You got something that looks like this, correct? Everybody get that graph? Okay. So here's the issue. The issue is as I'm approaching x equals -3, what does my limit say? Okay? What does my limit say? And anybody have an idea? What is the limit of this one? So what do I say? If there is no limit, I say does not exist. So this limit does not exist. Why? Why does this limit not exist. It's actually a really quite simple explanation. Good. Because remember, as you're approaching the x coordinate, the x value, it has to be the same as you're approaching it from the left and as you're approaching it from the right. However, on this one, as I'm approaching -3 from the left and as I'm approaching -3 from the right, look what happens. They're nowhere near each other, right? If the limit existed, my fingers should somehow meet. Okay, like on the last one. On the last one, on the last example, as I approached 2, my fingers met at 5. Okay? So here, the problem is, from the left and from the right, the limits do not exist because they're not going towards the same value. And remember, that's what a limit does, is what value is it trending to. Okay? So the limit is not the same from both the left and the right. It has to be the same from both left and right. Actually, it technically doesn't have to be the same from both left and right. But I have to be specific and ask. Do you guys remember how they ask limits? Only look at the limit from the left, or only look at the limit from the right. Good. There's usually like a plus or minus here. If it's a plus, it's asking it from the what? From the right. If it's a minus, they're asking it from the left, okay? So if it's specific and says only look at it from the left or only look at it from the right, then would this have a limit? Yeah, it would. But if it's not, that has to be from both sides. You guys remember that? Okay, right? So this is, remember, this is review. So you're probably used to looking at graphs like this. You're probably used to it when your teacher introduced limits to you. I know in the summer this is what we did. We had graphs that look like this. So I'm going to give you some time to copy this graph because looking at it like this is a great example. Okay, looking at this is a great example. All right, so I'll give you some time to copy this, and then we're going to go through all of these. All right, so it says here, use a graph of f shown on the right to decide whether the value of the given quantity exists. If it does not, find it. If it does, find it. If not, explain why. By the way, can anybody tell me what function this is, or what kind of function this is? This is a piecewise function, right? This is the definition of a piece. There is no equation that's all of this stuff put together, right? So notice it's just pieces. For if you wanted to kind of look, could you tell me what kind of function this might be? This is a rational, right? And then this piece right here is linear, and then this part right here, it's actually a version of a rational function, except the denominator is x squared, right? The denominator is x squared. It's funny because I had a student that came to tutoring and was like, what's the point of piecewise functions? Or why did they make piecewise functions? And if you think about it, you ever heard the old cliche, oh, mathematics is in everything, right? And mathematics, yeah, it was Caesar. I didn't want to call you out, but okay. That math is in everything. And the thing is that it's true, right? And I gave him the example of, think about a car, right? Think about a car. Now, the whole car is not a parabola, right? The whole car is not a parabola or a radical function, but the hood part might be because that's less wind resistance, right? So parts of the car are different functions at different times because that's the way they needed to be designed. So that's the point of piecewise functions. The point is, look, I don't need a parabola the whole time, or I might need a rational the whole time, but I need it for this little piece. You know what I'm saying? Okay? So, question A says f of 0. Guys, what is it asking for here? When x is 0, they want the y. So here, you're looking for a point. It is not asking for a limit. It's looking for a point. Okay, so when x is 0, I'm here, right here in the middle. But the problem is I technically have two parts, right? I have one above and one below. But remember, I'm looking for the actual point. The one above is a what? Is a hole. So I'm not looking up here. I'm looking where? Down. So then what is the value of f of 0? -4. Next one, it says f of 1. Again, I'm looking for a point. So I have f of 1. I only have one option down here. Okay, so does not exist. I understand what you're saying, but there's a difference in wording. When it comes to a point, you say a point is undefined. You say a limit does not exist. Okay, so this point is undefined. Okay, I understand you guys were all right, but it's all about semantics. It's all about wording. Okay, so a point is undefined. A limit does not exist. Okay. What about the limit? Now we're talking about limits as x approaches 0. Now I want you to pay close attention because it's 0. Is there any indication of left and right? No, so I need it 0 from both sides. So here is 0. Here's 0. As I'm approaching from the left, I'm writing this kind of curvy part. And as I'm approaching from the right, I'm writing this kind of linear part. And what's the problem? My fingers are not touching. They're not approaching the same value. So guess what? This limit does not exist. This limit does not exist. Okay? What about the limit as x approaches 1? Okay, the limit as x approaches 1. So here's my 1, and I am looking essentially from the left and the right again. So from the left, I'm writing this linear part. From the right, I'm coming down on this rational part. So as I'm going like this towards 1, are they meeting? Yes. So does the limit exist? Yes. What is the value of that limit? -1. So here's where a lot of students get confused. Because technically, there's no point there, right? But remember, the definition of a limit is what is it approaching? What is it trending to? So just because there is no actual point there doesn't mean that I can't be approaching that limit value. Does that make sense? Next one. The limit as x approaches -3 of f of x. The limit as x approaches -3. So here is -3. Okay? Okay, what happens at -3? What do I have? I do have an asymptote, okay? And again, I'm trying to get from the left and the right. So as I'm going from the left, I'm writing this top curve. From the right, I'm going down on this bottom curve. So what happens? They're nowhere near each other. So guess what? This limit does not exist. This limit does not exist. Okay? And then last one, the limit as x approaches 5. The limit as x approaches 5. So from the left, I'm writing this left curve. From the right, I'm writing this right curve. And I'm both going towards 5. What do you notice? They're getting closer, right? Are they ever going to touch this line? They're never going to touch. But so, and by the way, so this is continuing forever. What are they going towards? Because if it was 5, guys, it would be 5 here, right? So it's actually going up forever. They're going to continue to go up and up and up and up and get closer and closer and closer, actually never touching though. But what are they approaching? Infinity, more specific, positive infinity, right? Positive infinity. So is it possible for limits to go to infinity? Yes, it is, and we just saw an example right there. So any questions on how to read a graph to find a limit, right? All right, so let's get to my favorite one, okay? So we already know that we can, you don't have to copy this down. So we already know that we can find limits by graphing or using a table. But one of the easiest ways is to simplify, okay? Then solving by direct evaluation, simply plugging in. So if you can plug it in, then plug it in. So let me give you some very simple examples, okay? Because if, say I had this. Say I had the limit as x approaches 1 of 12x cubed plus x squared minus 1. Okay? The limit as x approaches 1 of 12x cubed plus x squared minus 1. So your first step should always, and I was doing it when we were finding it numerically, what do I always want to try and do first? Plug in. Plug in. So can I plug in this x? Yeah, it's not going to give, when do I get problems? And it's kind of like domain, what we were talking about. You really only have 2 issues ever with domain, okay? What are those issues? Rationals, meaning you can't have what at the bottom? 0, so you never want 0 at the bottom, that's an issue. And there's another function that gives you issues. Radicals, what do you never want in a radical? Even radicals. Negatives, you never want negatives in an even radical. If it was an odd radical, is a negative okay? Yes, it is, but an even radical, you never. So those are really your only 2 issues, okay? There are some others, but for the most part, Those are really your only two issues. So if it's not one of those function, odds are you're not going to have an issue. You're not going to have an issue. Same thing here. This is a cubic function, so I'm really not going to have an issue when I plug in 1. So guys, plug it in. 12, 1 cubed plus 1 squared minus 1. You shouldn't need a calculator. What do you get? 12. These are going to cancel, right? Because it's 1 minus 1, so that's 0. And basically 1 cubed is still 1. 12 times 1 is 12. So that's it. That's the answer for that one. Okay? You should be able to plug it in. The next one. Now, this is a rational function, is it not? This is a rational function. However, its the limit as x approaches negative 3. So if I plug in negative 3, is that an issue? No. Negative 3 on the bottom is fine. Now, if it was an x plus 3, then it would be an issue because negative 3 plus 3 gives me a 0, right? But here, simply plugging in negative 3, there's no issue with that. Okay, so negative 3 squared minus 2 times negative 3 over negative 3. Let's do some math. What is negative 3 squared? 9. And what's negative 2 times negative 3? So plus 6 over negative 3. 9 plus 6 is what? 15 divided by negative 3. So the limit as x approaches negative 3 of this function is equal to negative 5. And that's okay too. And the last one, basically, same thing. It is a rational. It is a rational function. So I might have an issue. But as x approaches 5, is there an issue? No. So simply 5 plus 1 over 5 plus 2. What do you get? 6 over 7. No issue. Okay? So this, you can find limits algebraically as long as there aren't any issues. Yes? So so like say this was x minus 5, okay? So good question, because that's the point. That's the point of this part of the lesson. You can't always do that. You can't always do that, right? So say, here we go. Say I have this limit here. I have the limit as x approaches 2 of 8 minus x squared, x cubed over x squared minus 4, okay? And he asked me, I'm sorry, help me, Jordan. I knew it was a J. I was like, it's either Jacob or Josh, but Jordan. Okay, so Jordan said, well, what happens if you can't plug it in? So here, my x is 2. Can I plug in 2 here? No. So 2 squared minus 4 would be 0, correct? 2 squared minus 4 would be 0. So what could I do? If I can't, I mean, I just showed you 2 different ways. I could perhaps look at the graph. I could perhaps make a table, right? Those will work. But there's a, I think, simpler and more fun way. It's algebraically. Okay, so since we can't plug in, so what we're going to try and do is we're going to try and factor and simplify. We're going to try and factor and simplify. So what I'm saying here is this. Maybe this function can be simplified to the point where I could plug in. Okay? So maybe I can simplify this to the point where I could plug in. All right? So what I'm going to do is look at this function independently. So I have 8 minus x cubed over x squared minus 4. Okay? Can you guys factor the bottom for me? Good. She said x plus 2 and x minus 2. Okay? X plus 2 and x minus 2. Is that correct? Okay? Does everybody know how she did that? She did the same ABC method, except in this case, what's my B? 0. So I was looking for factors of C that added up to 0, and positive and negative 2 definitely do that. Now, can I use that method on the top? No, I can't. No, I can't. Okay? So, first of all, does anybody else have an issue with the way this is written? So why? Why do you have an issue? because it's a negative x cubed. Not only that, yeah, does it make anybody else feel weird that the x cubed is second? I mean, it does to me too sometimes. Okay, so can we fix that real quick? How? Just switch them, right? So if I switch them, what would it be if I switch them? It would be a negative x cubed plus 8, okay? And even that kind of is an issue for me. Why? And Caesar said it. Because it's a negative x cubed, right? It's a Can I change that too? So Athenas is saying factor out a negative 1, right? Factor out a negative 1. If I factor out a negative 1, what do I have left? X cubed, now it's positive, minus 8. Good. X cubed minus 8. Okay, so that at least looks a little bit better for me. We okay? Now, can you factor that for me? How? Say that again. So you're in the right. So guys, there's actually a formula. Okay, so this is what you kind of have to remember, right? Because you don't get this on the calculus test. This is one of those rules. It's called the sum and differences of cubes. So basically, it's saying this: if your function looks like this, a cubed plus b cubed, then this is the factor of it. Okay, this is the factor of it. If the sum is a cubed minus b cubed, then this is the factor of it, okay? So I'm going to give you some time to copy that down, because we are going to use this. We are going to use this. And then we're going to see if it applies to the one we're doing right now. Okay, so what's the one I'm trying to factor? X cubed minus 8. That's what I'm trying to factor, right? Does it look like it's going to apply to one of these? Yeah, which one? The second one, which is the difference of cubes, okay? So what Carla was saying was this. 8, it just says 8, but look at what it wants. It wants b cubed, right? But 8, couldn't I express 8 as 2 cubed, right? So now, since I can, so these are the same thing. Now I can express, if I express 8 as technically it's 2 cubed, right? Doesn't it fit better into this formula? So what's my a? Just the x. And what's my b? Just the 2. So could you tell me what this is going to be in factored form? X minus 2 parentheses x squared plus, now it says a times b. In our case it would be 2x, right? 2 times x plus 2x, and then plus b squared. Our b again was what? 2, so 2 squared is 4. Okay? So now, let's go back, because that was the whole point we did this one. So really, this top portion is x minus 2 times x squared plus 2x plus 4. All of that over x minus 2, x plus 2. And thank you. Don't forget that negative 1 that we took out in the minute. It does make a difference. It does make a difference, okay? So now, remember, what was the whole point? We're going to factor and simplify, and we're trying to simplify to the point of what? So that we can cancel, so that I can plug in. So, do y'all notice anything here? The x minus 2's are going to cancel. The x minus 2's are going to cancel. So essentially, I'm left with negative 1 x squared plus 2x plus 4. All of that over x plus 2. And remember, this is the limit as x approaches 2. So now, look what happened here, Jordan. Now that I've simplified, factored and simplified, as I'm approaching 2, is there an issue anymore? No. The issue is gone. So 2 plus 2 is now 4. So guess what I can do now? Plug in. Now I can plug in. So negative 1, so it would be what? 2 squared plus 2 times 2 plus 4, all of that over 2 plus 2. Simple algebra here, guys. We can, 2 squared is what? 4 plus 4 plus 4, which is 12, but then it's negative 12 over 4, which is negative 3. Okay? So this is probably the one that you're going to use the most often, guys. And if you recall in pre-cal, we did this a lot. A lot of factoring to simplify. Factoring to simplify, okay? Most of you are good with the regular factoring, but you got to remember with this one when it comes to the cube function. So you have basically two formulas that are set up for you. All you got to recognize is that, is it plus or minus? Or is it plus or minus? And there is a difference in the formula if you're paying attention. The first part is plus and the second or minus, and then there's a minus here, okay? So, but other than that, they're not that much of a difference, okay? Any questions so far? Okay. Why don't you try this one? You try this one. Oh, you try this one. Okay, what's the first thing you probably did to help yourself out? Move it around, right? So that you could factor. If I move it around, so it would be a negative x squared plus 10x minus 9. But also I could do something else. Take out a negative. So if I take out a negative, that becomes a positive x squared. This becomes a negative 10. This becomes a negative 10, and this becomes a positive 9. Okay, and then on the bottom it's still x squared minus 1. And you guys are correct. I am going to factor. If I factor the top, what am I looking for? Factors of what? Of 9 that add up to negative 10. And what do you have for me? Negative 9 and negative 1. So it's x minus 9, x minus 1. And on the bottom, can you factor that one? X plus 1, x minus 1. So this one's x plus 1, x minus 1. Do you notice anything? The x minus 1's cancel. So essentially, you're doing the limit as x approaches 1 of negative x minus 9 over x plus 1. And here's the best part. There is no longer a problem, right? There is no longer a problem. There was a problem in the beginning. When I plugged in 1, it would be 1 minus 1, which gave me a 0 in the denominator. But now when I plug in 1, is there going to be a 0? No, it's actually going to be a 2. And if I plug in 1 on the top, 1 minus 9 is negative 8. But then it's a negative of that, so it turns it into a positive 8, which makes this a positive 4. Positive 4. Any questions on that so far? Any questions? Are you sure? Okay, because now it's going to get difficult. Okay? So, here we go. I have the limit as x approaches 3 of the square root of x plus 3 minus 3 over x minus 3. Okay, I have the limit as x approaches 3 of the square root of x plus 3 minus 3 over x minus 3. You guys remember seeing something like this? Do you remember how to do it? It's the same kind of situation. So first of all, can I plug in here? No. Okay, I can't plug in here because I'll get a 0 in the denominator. So do you see that I probably want to get rid of that denominator somehow, right? Probably want to get rid of that. So, what I'm going to do is I'm going to multiply this by 1. Okay? So now, hopefully you're saying to yourself, if you multiply it by 1, what's going to happen? It's going to be the same thing. And you're right. It is going to be the same thing. But I'm going to multiply it by a unique 1. Okay? Because remember, anything is 1 as long as it's something divided by itself. Correct? So, I'm going to multiply it by what we call its complex conjugate. Okay? So I'm going to multiply this by the square root of x plus 6 plus 3 over the square root of x plus 6 plus 3. Now I need you to verify, this is technically what? That's technically 1 because it's the same thing over itself. So I'm multiplying it by 1, right? Am I changing my problem then? No, because if I multiply by 1, nothing's happening. So now I'm going to uh, actually do it. Now, what is the only difference I just did? I changed it, right? And that's why I mean the conjugate. You guys remember that word conjugate? And that's exactly what it means. Conjugate just means it's the opposite sign, right? So if this one was plus, then this one would have been what? Minus. Okay, so now here's the hard part. How do I multiply this? How do I multiply this? Okay, so it's actually technically FOIL. You're actually going to FOIL because there are two things here, right? There's a radical minus 3 and then a radical plus 3. However, when it comes to something like this, so imagine, if you recall from Algebra 2, say you did x plus 2 and x minus 2, okay? Do you really have to use a full-on FOIL? Because what do you know that's going to happen? The middle part's going to cancel out, right? Because you're going to end up with a positive 2x and a negative 2x, and they're going to cancel. So really, all you're going to do is the front 2 and the back 2, and you'll end up with something like x squared minus 4, right? Okay? Does everybody see that the same situation is going to happen here? The same situation is going to happen here. You're going to end up, if you try and, I mean, can you FOIL all this? Yeah, be my guest. It's just going to make your life a lot easier. So what I'm going to do is I'm going to multiply the front 2, and then I'm going to multiply the back 2, because I know that whatever happens, the middle part's going to cancel out. Okay? So guys, what is the square root of x plus 6 times the square root of x plus 6? Just x plus 6. Why? What happened? The radicals cancel because technically it's by itself, right? So that's squared, and doesn't a square cancel out a square root, right? So then you're just left with x plus 6. And then what happens? What's positive 3 times a negative 3? Negative 9. Okay? So now, and then here's my recommendation on the bottom, because the bottom, it would actually be a real FOIL. It would actually be a real FOIL. Let's not do the bottom at all, okay? Because what did I say I wanted to do with this? Get rid of it. I wanted to eliminate the x minus 3, so I need it still to be there. So all I'm going to say is, look, I'm going to just keep the x minus 3 and write it like this. Okay? Because technically they're dividing. They're multiplying, right? I just didn't actually do it, but it is down there multiplied. Okay, let's simplify a little bit. What do I really have on top? X minus 3 okay, so I have the limit as that. So now do you notice why? Do you know why I told you to keep the bottom? Because look what happened. That cancels, and now here's where most students will make a mistake. What is left on top? Always a 1. There has to be something. So it's 1 over square root of x plus 6 plus 3. And remember, this is as the limit approaches 3. This is as the limit as x approaches 3. Is there an issue now? No, because x plus 3, so now x plus 6, which is 3 plus 6, which is the what? Square root of 9, which is 3, plus 3 is, so then this comes out to become what? 1 over 6. So although it says, I told you it's more difficult, it's really not. It looks more difficult, right? Looks more difficult, but if you understand the ins and out, it's really not that difficult, okay? But this only works out beautifully if you make this the right one, okay? Because you made it yourself, right? So make sure that if you put a minus here, then all the stuff I told you basically goes out the window, and you're still multiplying by 1, but it's totally different, right? Nothing's going to simplify the way you want it to. Any questions on that? Yeah, actually, so good question. It said only if the square root's at top? No, square root could be on the bottom too. The issue is, was there an issue in the first place? Okay? Like even if the square root was on the bottom, when I plugged in my x, did I get the 0? That was okay. And same thing will happen if the square root's up on the bottom. Okay? So, before we finish, oh, I thought I gave you one. Boo. Okay, so that's it. Yes, ma'am.